Hub. In today's class, we shall be discussing, today shall be our last class on set theory under MTH 101 Elementary Mathematics 1 as we have it in my school. It may not be the same course code or course title in your school. However, we shall be treating under this particular course our last class on set theory. Please feel free to go through all the videos we've made on set theory from the first class to the sixth class. Today being the seventh class, I shall be rounding up with discussions on precisely two items that we have to talk about before rounding up our class on set theory. So what shall I be discussing in today's class? So please take note, today is our last class on set theory. Okay, so precisely it is my seventh class on set theory. And what I shall be discussing today are two items, 1 and 2. Faith Jimmy Information System, thank you very much. Welcome to the class. I really appreciate. Thank you. Welcome. Thank you for reacting spontaneously. Thank you for reacting immediately to this class. So in today's class, I will be rounding up. Thank you very much. Well done. Thank you. So in today's class, I shall be rounding up my discussion on set theory. With two major discussions. So partitions of a set. I shall be defining and explaining what a partitions of a set are. Then I shall be discussing what we call Cartesian products of a set or of sets. Cartesian product of sets. Okay, so these are the two: Wizzy X, Wisdom Ekemini, Paul, Information Systems. Welcome to the class. Thank you very much. Thank you. I really appreciate. So these are the two items we shall be discussing in this class, being our last class on set theory. Immediately after this class, I shall be going into another topic you will be doing in MTH 101. Precisely, I'll be discussing number theory. So please feel free to join that class tomorrow by 9 p.m. Today I had to delay the class by 15 minutes because I had certain things to attend to. So please, if you haven't subscribed to the channel, do well to subscribe to the channel, smash a like on the video, and let us begin. So question number 1, that being said, let us start with partitions of a set. The question is, what is a partition? George Chuku Oko or Oko, good evening, welcome. Endurance Opeta, good evening, thank you very much. Welcome to the class, thank you. I really appreciate. So partitions of a set. This is our discussion for tonight. This video will be very, very brief. This class will be very, very brief. So as soon as I'm done discussing all these items, we are done. Okay, so let us discuss quickly what the partitions of a set are. Please feel free to ask me any question in this particular class. Oko Priscilla, welcome to class. Thank you very much for joining the class. So we are discussing partitions of a set. Sophie D, Precious Sector System, Information System, welcome to the class. I acknowledge all of you. Thank you very much for your support. I'm very grateful. Welcome. So we shall be discussing partitions of a set, and there are two definitions I want to take. So let's start with partitions of a set. So how do we define what is called the partitions of a set? Okay, so I'm going to say definition: let X be a non-empty set. Okay, and please take note, if we call X, this set X, capital X, a non-empty set, it means that there are elements in the set. So the word non-empty means that it is actually not empty. Oga Joe, welcome to class. Thank you very much. Thank you. Information System, you guys are wonderful. You guys are the best. Thank you very much for joining the class. I salute you all. So what is a partition of a set? Now, for us to define the partition of a set, we have to start with saying that there is a non-empty set X. Okay, and by non-empty we mean that the set actually contains elements. For example, if your house is non-empty, it means that your house has persons inside the house or has items inside the house. So let X be a non-empty set. Then the question is, what are partitions of X? We can now say partitions X are a set of non-empty, what we call partitions of a set. Emmanuel, Eni, welcome to class. Thank you very much. Information system, you guys are the best. So partitions of X are a set of non-empty subsets. So we have discussed subsets of a set. So what we call partitions of a set are a set of non-empty subsets of X. The set X we called non-empty in the very beginning, such that Victor Ibanaidet, welcome to class. Good evening. Information system, welcome. Such that every element small x that is a member of X is a member, let me put this into frame, is a member of only one subset. It's a member of only one subset. Okay, Victor, you just joined in. Please, sir, what is the topic? Alien Divine, welcome. Biochemistry, good evening, welcome. So, Victor, the topic is partitions of a set. Partitions of a set and Cartesian product of set. These are the two things we are discussing in today's class, and this is my 7th class and the last class on set theory. So after this class, we are moving to a new topic called number systems. We are moving to number systems. So this is my topic, partitions of a set and Cartesian product of sets. Okay, so I'm starting with partitions of a set, and I am saying let X be a non-empty set. Partitions of X are a set of non-empty sets, subsets of X, such that every element small x that is a member of X, the non-empty set, thank you very much, Victor, thank you very much, is a member of only one subset, subset, and none of the subsets are empty. Okay, so this is what we define as the partitions of a set. Okay, now this is what, before we proceed to something more mathematical about this definition, let me explain what this means. Let's use a layman definition. Let's assume that this is your household. So let's assume that in this household there are several persons in the house. Let's assume that this is a household comprising several persons. Okay, now if this is the set X, guys, if this is the set X, we are discussing what we call the partitions of this set X. Now you see, every member, everybody in this class are elements of the set X. So we can call everybody in this class, this guy, this guy, this guy, this guy, all of them, we can regard them as small x. So all the small x are members of capital X. That's what we are trying to say. Now, if all these elements are if all these objects here are elements of the set X, the question is, what is a partition? What are partitions of X, this non-empty set? Clearly, the definition says that for us to talk about partition of a non-empty set or a partitions of a set, that set whose partitions we want must be non-empty. I repeat, for us to talk about the partitions of a set, say X, the set X must be non-empty. Non-empty means that it must contain elements. Now, the partitions of a set, the rule is a partition of a set is a subset of the non-empty set X, such that if you consider all the partitions, if you consider all the subsets called partitions of X, none of them must be empty. None must be empty, and none must contain elements that have already shown up in other sets. So let's assume that we call this guy number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, and number 9. Now, I can draw up 3 partitions of this set. One partition could be the one that takes 1, 2, 6, and 7. And the second partition will be the one that contains 4 and 3. While the third partition will be the one that contains 5, 8, and 9. Why is this particular set? Now you will notice that if I segment X into 3 partitions to show that it is indeed a partition. Take note, this first set here, this first set is a subset of X. This first set is a subset of X, and it is a subset that is not empty. This second set is a subset of X, and it is also not empty. This third set is a subset of X, and it is also not empty. So the first subset contains 1, 2, 6, and 7. The second subset contains 4 and 3. The third subset contains 5, 8, and 9. Now, this particular set, this one, okay, so let me repeat what I said last before I was interrupted by poor network. Please take note, I am saying that if something is a partition of a set, that set, number one, whose partitions we want must be non-empty. It means that it must contain elements. Number two, if you partition a set that is non-empty, you will be partitioning it into subsets. And the rule is that for each of those subsets to be called a partition, 2 things must happen. One is that each of the subsets must not be empty. They must contain elements. Number 2, each element that is found in a set must not repeat in another set. So, that being said, let us go over the definition again. Let X be a non-empty set. Partitions of X are a set of non-empty subsets of what? X. Just like this one. We have formed 3 partitions of X, and each of them are non-empty. Number 1. Number 2, each of them contain elements that you cannot find in any other set but themselves. In the set that contains 1, 2, 6, and 7, you cannot find 1 in the second set, you cannot find 1 in the third set. In the set that contains 1, 2, 6, and 7, you cannot find 2 in the second set or the third set. Neither can you find 6 and 7 in the second set or the third set. You cannot find an element 8 which is in the... That being said, let us now go over to the 3 conditions. So we can now say number 1, if a set or a set of sets, subsets are partitions of a set X, then number 1, please take note, if Pi is a partition, if Pi is a partition of X, then Pi must not be what? Empty. Okay? It must not be empty. If there are n partitions, that is I equals 1, 2, 3 to n. Partitions of a set X represented as Pi. So Pi when it is 1 will be partition. Pi when it is 2 will be partition 2. Pi when it is 3 will be partition 3. Up to Pi when it is n will be partition n. We are saying that rule number 1, if Pi is a partition of X, it must not be empty. So partitions of a set are not empty. Number 2, if Pi is a partition, then Pi when it is 1 united with Pi when it is 2, united with Pi when it is 3, united with, and it goes on to united with Pn when Pi when it is n. If you unite every partition, of a set that is non-empty such as X, then the union should give you X. So the union of all partitions of a set must give the set itself. Okay? Then number 3 is that if Pi is a partition, there can be for every I, there must not be a Pj that is equal to Pi. So it means that P1 cannot contain elements that are found in P2, neither can P2 contain elements that are found in P1. So all the sets are exclusive, mutually exclusive. And that means that if I is not equal to J, then Pi intersection Pj must be empty. Okay? So the intersection of any 2 partitions of a set must be empty. Guys, for those of us just joining the class, or for those of us that will be watching this video later on, what are we discussing? We are discussing partitions of a set. And I'm saying that for us to talk about partitions of a set, the set whose partitions we want must be non-empty, meaning that the set whose partitions we want must contain elements. Number 2, if we are talking about partitions of a set, the partitions of a set drawn from they must be subsets of the set itself, which is non-empty, such that no two partitions will contain the same element. Okay, and no partition must be empty, and the union of all the partitions must give the non-empty set whose partitions we have already developed. So those are 3 things you must note about partitions. Now let's take an example. I'm going to take an example number 1 under this discussion. So let's assume we have a set X, and this set contains 1, 2, 3, 4, 5, 6, 7. Okay, now if I have X to be a set that contains 1, 2, 3, 4, 5, 6, 7, it means that X is non-empty. Now if I form 3 subsets, Samuel, Ina, greetings. Okay, I'm Sunday Samuel. Good evening, welcome to class from Information System. Thank you very much for joining the class. Thank you very much. So now let's assume that we have X to be a set that contains 7 elements, 1, 2, 3, 4, 5, 6, 7. Now we can form 3 partitions of X, A, B, and C, such that the first partition contains 1, 3, and 5. The second partition contains 2 and 6. The third partition contains 4 and 7. These are clearly partitions of X. Why are they partitions of X? The reason why you can boldly call them partitions of X is because you will notice that number 1, according to our rule above, our rule says we should check if they are partitions of X. It means that each of them must be non-empty. So I can call this first one that I'm calling a partition P1. I can call this one P2. I can call this one P3. So there are 3 sets that I'm calling a partition of X. I want to check if they are partitions indeed. Now, rule number 1 says each partition must not be empty. Look at it very well, guys. P1 contains 1, 3, 5. P2 contains 2 and 6. P3 contains 4 and 7. Are they empty? The answer is no. So they are not empty, and it means that they have satisfied condition number 1. Condition number 2. Yeah, greetings, Samuel. Thank you very much. Condition number 2 says if the non-empty sets, you are calling a partition are indeed partitions, then their union must give the set itself X. Now let us see. Rule number 2. So our PIs for rule number 1 are not empty. Okay, so this one is checked. Rule number 2 says that P1 union P2 union P3 as it is must give us X. Is that so? The answer is a big yes, because when I unite 1, 3, 5, the first set, with 2, 6, the second set, and I unite it with the third set, 4, 7, the answer I will get for this union is X, because if I unite 1, 3, 5, 2, 6, 4, 7, it is going to give me X. 1, 2, 3, 4, 5, 6, 7. So that second rule is correct. That is this one. Okay, that says that the union of every partition must give the set itself X. So this is indeed looking like a partition. Let's now see number 3. So number 3 condition. What does number 3 condition say, guys? If a set of subsets are partitions of X, then if I is not equal to J, then Pi intersection Pj must be empty. Now look at it clearly. You will notice that P1 intersection P2 is an empty set because they have nothing common. You will notice that P1 intersection P3 is equal to empty set because they have nothing in common. Likewise, P2 intersection P3 is also empty because they have nothing in common. So guys, looking at this example, is it difficult? The answer is a big no. And is this a partition? The answer is a big yes. So A, B, C are partitions of X. Now let's take an example using this. What if I decided to do this? If I develop 3 sets or 2 sets, would we have been able to call these 2 sets if we had developed subsets from X? The question is, are they subsets of X? The answer is yes. Question 2. Do they fulfill the first condition that all the subsets of X must be non-empty? The answer is yes. They fulfill the first condition. However, if the subsets of X are partitions, not only must they fulfill the first condition, they must fulfill other conditions. Now, condition number 2. If you unite E and F, will it give you X? The answer is yes. Where does E and F fail to be partitions of X? They fail in rule number 3. Rule number 3 says their intersection must be empty. However, you will notice that the intersection of E and F is not empty, because intersection of E and F gives you a singleton, which is in this case 4. So because they have an intersection which is not empty, it means that E and F are not partitions of X. However, A, B, C are partitions of X because they satisfy condition number 1, condition number 2, and condition number 3. So if a set of subsets are partitions of a set, then you must take note of them satisfying all the rules. They can't satisfy 2 and leave 1 out. They must satisfy all the rules. And that is it about partitions of X. Now please, if you have questions on partitions of X or partitions of a non-empty set, please let me know in the comment section. You can ask any question you want to ask. I have told you today's class will be very, very brief because it is my last class on set theory and I'm busy discussing items we failed to discuss. So what did we start with discussing? Just in case you are joining the class just now, we are discussing our 7th class. We are discussing our 7th class on set theory and our last class on set theory. And we are discussing 2 items, partitions of a set and Cartesian product of sets. So we have just finished discussing number 1 and we are moving over to the next topic, Cartesian product of sets. So let's move over to the next topic. Okay, let's move over to the next topic, Cartesian product of sets. So quickly, let us now see what is the Cartesian product. What are Cartesian products? Cartesian products of sets. So I'm going to go as follows. A Cartesian product of 2 non-empty sets. A Cartesian product of 2 non-empty sets is the collection. It is the collection of all ordered pairs. It is the collection of all ordered pairs obtained by the product of the 2 sets. Okay? So, simply put, what we call the Cartesian product of 2 non-empty sets is the collection of all ordered pairs obtained by the product of the 2 sets. I'm going to show you what an ordered pair is. Now, mathematically, we say that let A and B be 2 non-empty sets. Non-empty sets. Okay? Then A times B, called the Cartesian product of A and B, is the set of all ordered pairs A, B, such that A is a member of A and B is a member of B. Now, by ordered pair, we mean that the first element from the first set is placed first before the second element from the second set. So all ordered pairs, starting with taking elements from this and pairing with elements of the second, provided the first element is from the first set and the second element is from the second set, is called a Cartesian product. So if you want to look at it again one last time, a Cartesian product of 2 non-empty sets is the collection of all ordered pairs obtained by the product of the 2 sets. And if A and B are these 2 sets we are talking about that are non-empty, then A times B, which is read as the Cartesian product of A and B, is the set that contains all ordered pairs, such that A in the ordered pair is selected from the set A and B in the ordered pair is selected from the set B. Now let us take an example to round up this class. So example 2. Okay, so example 2. Let if A is equal to 1, 2, a set that contains 1, 2, clearly it is non-empty, and B is a set that contains 1, 2, 3, and 4. Then the question says find A times B. Find A times B. So if you are to find A times B, that is the Cartesian product of A and B, solution is as follows. Guys, it is very simple to solve problems on Cartesian product. It is very, very simple. So what you will do is to say A times B is equal to, take the first element 1, okay? Take the first element 1, and when you take the first element 1, pair it with the second element. So I'm going to start with 1 in A, I'll put it, comma, I'll take 2 in B, okay? That is my first ordered pair. The second one, I'll take 1 in A and pair it with 3 in B. I will go again with 1 in A and take 4 in B, okay? Then I will go again to take 2 in A and then B. I will take 2 in A again and 3 in B. I'll finally take 2 in A, 4 in B. And this set is called the Cartesian product of A and B. This result you have just obtained is called the Cartesian product of A and B. Now let us look at another example. I told you it is very, very simple. It is not difficult. So if A equals a set that contains orange and apple, and B is a set that contains mango and guava, then the question is A times B. What would A times B be? A times B will be the Cartesian product of A and B. What would you do? A times B would be the set that contains orange first before mango. So take orange from the first set and pair it with mango. Second, take orange again. Take orange and pair it with guava. Then next, take apple and pair it with mango. So I'm going to be having apple, mango, and finally take apple and pair it with guava. So this set you have just formed is called the Cartesian product of A and B. It is that simple. Now please, please and please make sure you do this for me and let me know your answer in the comment section. Example number 3. Example number 3, please guys, answer this question and drop your answer in the comment section. I will reply yes or no whether you are correct. So example number 3 is for you. Exercise. Now please tell me if A is a set that contains I, O, E, U, V, and I have a set x1, x2 such that x1 contains I, O, E, and x2 contains U and V. The question is, are x1 and x2 partitions of A? That is my first question. Watch this video all over again and answer this question for me. Watch the video from start to finish and try to answer this question. Drop your answer yes or no in the comment section and give reasons by means of comment. Example number 4. I have 3 of them for you. Example number 4. Example number 4 says if X is a set that contains 4, 5, 7, 9. So question number 4, example 4 says if X is a set that contains 4, 5, 7, 9, 3, 2, and 10, then A is a set that contains 4, 5. B is a set that contains, is a subset of this set X that contains 9, 10, and 3. And C is a set that contains 7, and 2. Okay? 7, 2, 3. Good. So C is a set that contains 7, 2, 3. The question I have for you guys are A, B, and C partitions of A or partitions of X? Are these 3 sets partitions of X? please answer the question and drop your comment in the comment section. That is what I'm giving to you to do. The last question is example 5. All these questions I'm giving you, please watch the video all over again and drop your answer in the comment section. Not immediately, but subsequently. Once you are done watching the video, drop your answers to these questions in the comment section. They may come out in your exam. Please take note of that. So if what do you call it, A is a set that contains 4 and 5, and B is a set that contains 2, 3, 4, please find A times B. Okay, find A times B. And number 2, find B times A. Please, answers to this question, watch the video from start to finish and drop them in the comment section, possibly tomorrow or tonight, and I'm going to reply as usual, yes or no, whether you are correct. Please, is there any question? If there's any question, all of you watching, you guys are legends. You are legends. Thank you very much for joining this class. You are so wonderful, and I really appreciate all of you. Please smash a like on this video and endeavor to share this video to your colleagues. Share it to all platforms where your colleagues belong, and invite them to tomorrow's class, where we shall be beginning a new topic, number systems. Thank you very much. In the absence of any question, in the absence of any other comment, please like the video, share this video, and subscribe to the channel if you haven't subscribed. God bless you. Good night.